All right, today we're going to talk about what is maybe the most important, most famous shape in all of statistics. Its official name is the normal distribution, but you've probably heard of it as the bell curve. And trust me, once you really get what it is, you are going to start seeing it absolutely everywhere.
So let me start by asking you a question. What could things like test scores, or the height of every person in a crowd, or, get this, even the results of flipping a coin 1,000 times, what could they possibly have in common? I mean, they sound totally unrelated, right?
Well, here's the surprising, kind of cool answer. When you collect enough data on any of those things, they all start to form this exact same elegant shape. Yep, that's the bell curve. And it's not just some abstract math concept. It's a fundamental pattern that's basically woven into the fabric of the world. So let's properly meet the bell curve. We're going to break down what makes it tick, and you'll see pretty quickly just how much power is packed into this one simple shape.
Okay, so its fancy official name is the normal distribution. Sometimes you'll hear people call it the Gaussian distribution, but really all you have to do is think of it as a picture that shows you how a bunch of data points are spread out. And the two most important words to remember here are symmetric and bell-shaped.
The real beauty of the bell curve is just how simple and elegant its properties are. First, it's perfectly symmetric, which just means the left half is a perfect mirror image of the right half. It also has just one single peak right in the middle. Statisticians call that unimodal. But here's the really amazing part. That single high point represents three different things all at once. It's the mean, which is the average, the median, which is the middle value, and the mode, which is the most common value. They all line up perfectly in the center. Pretty neat, right?
You know what's wild? To describe any bell curve in the entire universe, you only need two numbers. That's it, just two. These two parameters control its exact shape and where it sits on a graph. So let's meet them. First up, we have the mean, which you'll see written with the Greek letter mu. This one's easy. It's the location parameter. Think of it like an anchor. It tells you the exact spot on the number line where the center, the peak of the bell, is located. The second parameter is the standard deviation, represented by the Greek letter sigma. Now, if the mean is the anchor, the standard deviation is the stretchiness parameter. It's all about the spread. A small standard deviation means all the data is clustered really tightly together, which gives you a tall, skinny curve. A large standard deviation means the data is spread way out, and that results in a short, wide curve. And you can see this perfectly right here. See the pink curve? Its center is shifted over to the left because it has a different mean. Now look at the red, green, and blue curves. They're all centered at the same spot, at 0, but their shapes are totally different. That's the standard deviation doing its job, making some tall and narrow, and others, like that blue one, wide and flat. So just remember, mean sets the location, standard deviation sets the spread.
Okay, so now that we've got the anatomy down, let's get to the single most useful shortcut for actually reading and interpreting a bell curve in the real world.
Officially, it's called the empirical rule, which sounds a little formal, but you'll remember it by its much catchier nickname, the 68-95-99.7 rule. And this is such a powerful mental shortcut. Here's how it works. You start at the center, at the mean. If you take one big step, that's one standard deviation, out to the left and to the right, you've just captured about 68% of all the data. Now take two steps out in both directions. Boom, you've now accounted for 95% of the data. And if you go three steps out, you're at 99.7%. That's pretty much everything.
And this predictable pattern is what makes it so useful. It doesn't matter if we're talking about IQ scores, blood pressure, or even errors coming off an assembly line. If the data follows a bell curve, this rule applies. It's an incredibly fast way to get a feel for how spread out everything is. But what happens when you want to compare data from two different bell curves? For that, we need something that acts like a universal translator.
Exactly. Think about it. How can you really know if a 1400 on the SAT is better or worse than a 30 on the ACT? They're on totally different scales, right? They have different averages, different spreads. It feels like comparing apples to oranges. But, of course, statistics has a really clever way to solve this.
The solution is to convert everything to one universal benchmark. We call it the standard normal distribution. And it's just a special kind of bell curve that is always centered at a mean of 0, with a standard deviation of 1. It becomes our common yardstick for everything.
And we do this conversion using a simple little formula to calculate what's called a z-score. All you do is take your score, subtract the average for that group, and then divide that result by the standard deviation. This one calculation translates any value from any bell curve onto our standard universal scale.
So what does a z-score actually tell you? Well, it's just the number of standard deviations your score is away from the average. A z-score of 1.5 simply means you're 1.5 steps above the mean. A z-score of -2 means you're 2 steps below it. And this is where the magic happens. This standardization unlocks the world of probability. The shaded area under any part of the curve can now tell you the exact chance of a result falling in that specific range.
Okay, let's bring it all home. We've met the curve, we know its anatomy, we've even found its universal translator. But so what? Why does this one shape matter so much in the real world?
Okay, so why does this all matter? First, it simplifies things. It lets us take a messy cloud of data and boil it all down to just 2 numbers, the mean and the spread. Second, the empirical rule gives us that instant mental shortcut to understand how the data is distributed. Third, z-scores act like a universal translator, letting us compare completely different things on the same scale. And finally, all these tools together make the bell curve the absolute foundation for most modern statistics.
And that just leaves us with a final thought. The bell curve isn't just some idea in a textbook. It's a real pattern that describes how the world works. So now that you know what to look for, how many examples of it are you going to start noticing every single day?